Hi everyone, and welcome to this new video about steady-state analysis. And we start with our third example about RLC circuit in steady state. And in this example, we will analyze this circuit using mesh current analysis. So we have done in the example number 1 and number 2 using node voltage analysis, so nodal analysis. In this example, we will use a different method to illustrate also the mesh current analysis. What do we have? We have two voltage sources, VA and VB, and an inductor, one resistor, and one capacitor. The values are shown here. As you can see, the voltage sources are shown in time domain, and we have for the voltage source VA and also for the VB 1000 radian per second at the frequency. It is exactly the same. It must be also that it's mandatory to carry out the calculations in steady state. If this were different, then we should use different methods like Fourier series. That is not the topic for this example, so we have exactly the same frequencies. So the following is required. Calculate the following: steady state voltage across the resistor, steady state voltage across the inductor, steady state voltage across the capacitor. So actually what they want is calculate for each element the steady state voltage. So we need to determine VR, VL, VC, of course, in time domain. Now before we start, we would like to convert everything in the frequency domain. So I would like to determine the reactance of the inductor, reactance of the capacitor, and also I would like to represent the voltage sources VA and VB in frequency domain. So I will start with that. So I will have V of X of L, which is the reactance of the inductor, omega times L, and I have the omega as 1000 times the 3 millihenries will give me 3 ohms. Now for X of C, for the capacitor, will be 1 over omega times C, and I will substitute the value, will be 1 over 1000 times 200 will be 2 times 10 to the minus 4 is exactly the same, and this will result in 5 ohms. So I have now for the reactances these values. For VA, which is a vector, so with the phasor representation in polar form, I will have the amplitude, which is 5, and I have a phase of 0 degrees, as you can see. Now for VB, which is also in cosine form, so I can take the amplitude 8, and the phase will be minus 30, both in volts. Okay, that's actually for the reactances and the polar representation of the sources. Now the next step is actually determining the mesh currents. So we will like to carry out the mesh current analysis, and I will now define a mesh in our circuit. So what I want is I would like to make the mesh like this. So for the left side I will make the mesh like this, and I will denote this as A1, which is the vector current A1, and this one is A2. Okay, so I will have to develop the currents equations for mesh 1 and mesh 2. For mesh 1, what do I see? I see actually this voltage source applied actually across this voltage as this element and this element. So what I have is the following: I will have minus VA, because I start at the bottom from the ground, and then I make a circle and I come back at the same point, which is minus VA plus, now I have the I1, which is in the same orientation for inductor and the resistor, so it will be R plus, again in the frequency domain, in the complex representation, times I1, but I2 will be of course in the opposite direction, and it will be minus R times I2, and this will be 0. Now if you now write this in a different form, such that you have the voltage at the right side and the parameters in the right order, I1 and I2, at the left side, you will have the R plus J times X of L I1 minus R X of I2 is equal to V of A. Now I will do now the same for mesh 2, but before I do, I will substitute also the values here. So what do I have is the following: R was given as 4 plus J was calculated XL with 3, so I will have this. And I1 minus was 4 again for R, I2. And the value of VA is given in Phasor notation, and polar representation is 5 at the phase of 0 degrees. Okay, now this is actually our equation number 1. Now I will now move to develop the equation for mesh 2, which is I2. How do I start? Again, I can start here, but the positive orientation is I2 in this case, so I will have R minus, because it is a capacitor, minus J XC, so I will have the following, I will write it down. So it is R minus J XC times I2, and then minus, which is in the opposite direction for R1, for I1 I mean, and plus VB, which is 0. So what I have is the following: I2 will be in the same direction for R and C, but for I1 I will have opposite direction here, so I1 will be in this direction, I2 will be in this direction, so I will have a minus R times I1, and the VB will be positive because I will start here and then come back again at the ground. So I start at the ground, make a loop, and come back at the same point, which is the ground. And if I now rewrite this, as we did for example for mesh 1, I will place the VB to the right side and I will set this in the right order from I1 and I2. What do I have is the following: I will have the minus R I1 plus R minus J X of C times I2, which is minus VB. Now if I now substitute the values, I will have minus 4 I1 plus 4 minus J 5, which is X of C, times I2, which is minus 8 phase minus 30 degrees. Now this is actually our second example, a second equation I mean. What do I do now? What can we do as a next step? Now there are different methods to calculate the values for I1 and I2, because if I know the I1 and I2, then actually I can carry out the calculation to determine the voltage across this resistor, and also voltage across this inductor, and also voltage across this capacitor. So what we can do is we can develop, of course, a matrix, but we can also make a back substitution by expressing one of the elements in one of the components, one of the unknowns, and substituting that in the other. So I will follow the last procedure. So what I want is the following. I will have this expression written in a different form, so I will make this clear. So I will have it like this. I will have 4 times I1. So I will place this at the right side and this one at the left side, and I will swap the equation. So I will have 4 times I1, which is 4 minus J 5 times I2 plus 8 times minus 30 degrees. Okay, that's actually the expression. Now, the problem now here is I cannot add a rectangular expression with a polar expression. So what I want, what will be helpful is represent this in the the rectangular expression, so I can add the terms together. That's actually what I want to do now. So actually the next step is convert this 8 minus 30 degrees in rectangular representation, which is actually this one. So I will write it down again. So it will be 4 times I1 will be 4 minus J5 I2. And if you do math here, you just convert this from the polar to rectangular representation. We have this done this many times. It will be 6.93 minus J4. That's just analysis, and I have now a representation actually for I1 in terms of I2. Before I can do that, I will divide everything by 4. So left side and the right side of this equation I will be divided by 4 will be 1 minus J, each term will be divided by 4 will be 1.25 times I2 plus 1.73 minus J. And I will now denote this as equation number 3, and I will use this. What will I do? What will I do next? I will do the following. I will substitute this expression. So equation number 3 will be formula number 3 will be substituted in formula number 1. So I will write it down. Substitute 3 in 1. What do we get? Now we get the following: 4 plus J3 times I1. I mean, that's actually what I have to substitute. So that's actually the whole business here must be substituted in this. So I will have 1 minus J 1.25 times I2 plus 1.73 and minus J, and I will close the brackets, and I have also minus 4 times I2, which is this expression, and I can also convert this to rectangular expression, which is actually 5 plus J0, which is just 5. So if I now move to the rectangular representation, I will have this. So if I now calculate this out, just working the parentheses and the brackets, you will have the following expression in a final form. So you will have the, maybe I can do it step by step. It is not really that difficult, but it will be helpful if you see it also. So it will be 4 times J squared J3 times 1 minus J 1.25 I2, and exact same for the next part. Will be 4 plus J3 times 1.73 minus J, and then minus 4 times I2 will be 5. So what I did is actually I had this term, I multiplied inside with this term and also with that term. If I now multiply this out and rearrange everything, I will have the following expression will be 3.75 minus J2. So I will group every term with I2 together, and I will place all the constants and imaginary parts which is not related to I2 to the right side of the equation. I will have the minus 4.92 minus J 1.19. Okay, that's actually the expression what we have now. Now, for calculation of the I2, it will be helpful to represent this also in the polar form and also this one, so the division will be much easier. So if I now convert this and this in polar representation, it will be 4.25 phase minus 28 degrees times I2, which will be equal to 5.06, and the phase will be minus 166 degrees. Now finally I2 will be 5.06 phase minus 66 degrees divided by 4.25 phase minus 28 degrees. Now what do you do next? You divide the magnitudes. So 5.06 divided by 4.25, that will be the magnitude. So that's actually the 1.19, and the phase, associated phase, is minus 166 degrees minus because you divide it and you do minus 28 degrees will be plus 28 degrees, and this will result in minus 138 degrees, and it will be in amperes. Okay, now I have now the I2, and I can also represent this in the rectangular representation, which will be handy later on. And this will be, if you do the math again, you will have minus 0.884 minus J 0.996 amperes. Okay, now I have the polar representation and also the rectangular representation for I2. If I now want I1, what do I need? I need actually this expression. Let me move to the left. I need actually this representation, because I have now I2. I can now go from I2 to this expression, which is I1. So if I now substitute this expression in this, or this expression, it doesn't matter, in this, I can now carry on the calculations again. So if I now do that also, then I1, which is 1 minus j 1.25 times this, just substitute this, the rectangular expression, so minus 0.884 minus j 0.796, that's actually for the first, and then plus 1.73 minus j. Now if you now rewrite, simplify this, combine the real parts and the imaginary part, etc., you will have the following. You will have minus 0.149 minus j 0.691 amperes. And if you convert this to the rectangular, the polar representation, you will have 0.707 phase minus 102, and is actually also in amperes. Okay, now we have now two currents, the mesh currents determined I1 and I2, both in the rectangular and the polar representation. Now the job is to determine the currents for each element, because if I know the current, I can use Ohm's law and use the resistor value and the reactances of these elements and calculate the voltages, which is actually the required situation in this case. So if I now want to know what is actually the current through R, and current through inductor and current through the capacitor, it's just simple, because I1 is the current through the inductor and I2 is just the current through the capacitor. But I1 minus, because this is actually circling like this, minus I2 will be the current through the resistor. So if I now move to the next part of my analysis, it will be the current. So if I now make the following, the IL will be I1, IR will be I1 minus I2, and IC will be I2. That's actually the situation for our analysis. So if I now write down IL, what is IL? IL is just write down what I1 is. I will use the phasor notation, so it will be this one. For I1 I will take this, so I will have 0.707, so I will be 0.707, and a phase will be minus 102, so minus 102. Okay, that's actually for the current. Now for the other one, I will have to do the subtraction, so I will have minus I1 minus I2, so I will again use these values, and I2 is shown here, which is 1.19 and a phase of minus 138. Again, if you do the math here to transform the polar to the rectangular and add the real and imaginary parts, you will have the current and also convert to the polar representation for the IR, which is 0.742 and a phase of 8.1 degrees. That's for the resistor. And for the capacitor I2, which is the value of 1.19 phase minus 138 degrees. And that's actually the values for the current. So I will make this clear, this for the current. Now, next step, voltages. For the voltages, I need for VL, I need the IL, and I also need the J times XL. And I again use the polar representation directly in this analysis. So what do I have? What is IL? IL is already given here, so it is 0.707 phase minus 102, and the value of XL was given, already calculated, was 3, but the phase orientation is plus 90 degrees. So if I do the math here, multiply the magnitudes, add the phasors together, you will have 2.12 phase of minus 12, and that will be in volts. Now the next one, VR, which is IR times R, and that will be, if you look at the current IR, will be 0.742 phase 8.1 degrees. Now the value of the resistor was already calculated, which was, it was already given, shown here above. Let me look at it again. So it was given, this was 4 ohms, so 4 phase 0 degrees. So you will have 4 phase 0 degrees, and this will result in 2.97 and a phase of 8.1 degrees in volts. Now the next one, the last one, is the capacitor, will be I of C times, and this will be minus J times X of C, so be careful. Let me make this clear. Okay, and IC I know, that's 1.19 phase minus 138 degrees, and the capacitor value we have also calculated that it was 5, so I will have 5 phase minus 90 degrees to convert this directly in the polar representation. If you do the math here also for the capacitor, you will have 5.95 phase of minus actually 228 degrees in volts, but you can also add 360 degrees for the phase, then you will have the expression like this, 132 degrees for volts. Now I have now all of them in the complex representation in polar, and I would like to convert this to the time domain. I am actually done. So in time domain, what do I have? So time domain, that's the next part. So that will be for VL, will be 2.12 cosine again, and then 1000, and it will be minus 12 degrees and volts. That's actually the representation for the VL. For VR, I have 2.97 cosine 10 to the power 3 t, and then plus 8.1 degrees in volts, and the capacitor, the last one, will be 5.95 cosine 10 to the power 3t, and then plus 132 degrees in volts, and that's actually the whole business. So we have done the complete situation for this example.